Maximum and minimum problems. From a 30 centimeters by 30 centimeters sheet of cardboard, so here's our sheet of cardboard, 30 centimeters by 30 centimeters, square corners are cut out so that the sides are folded up to make a box. So the square corners, 4 of them, are cut out, and what's left can be folded to make this box. Question 1. What dimensions will yield a maximum volume? And question 2. What is the maximum volume of the box? So what dimensions? So that means length, width and height. We're trying to find the dimensions, the measurements that will give us the maximum volume. And then for question 2, we just work out the maximum volume. So when you have questions and they ask you about maximum or minimum, whether it be volume or area, you want to think differentiate. So we know that the volume of a cube or a cuboid is the length multiplied by the width multiplied by the height. So we need to come up with the dimensions of this box. We need to come up with the length, the width and the height. So since square corners were cut out, we can label this length here as x. So if it's a square corner, if this is a length of x, then this is also a length of x. And when this shape is folded together, these two lengths will actually go side by side. So that's why we have this labelled as x here. So if we were to fold this shape up, this length here and this length here, so these two sides would end up being stuck together and they would form the corner of this box. So we can call this the height, or just h. Okay, so we also need to work out what this length is here in blue. So if from this corner right away the way across to this corner is 30 centimeters, and we know that from here to here is x, then from here to here is also x. And if from here to here is x, then from here to here is also x. Then this blue part is going to be 30 minus x minus x, which is going to be 30 minus 2x. So the base of our cuboid will be 30 minus 2x. So each of these blue parts are going to be 30 minus 2x. So the height is x, the width is 30 minus 2x, and the length is also 30 minus 2x. And we know that the volume of a cube or a cuboid is the length multiplied by the width multiplied by the height. Okay, so question 1, what dimensions will yield a maximum volume? So we've labelled our dimensions as x, 30 minus 2x and 30 minus 2x, but we actually have to figure out now what the actual values will be. So we know that the side length in the base is 30 minus 2x and that the height is x. And we know that the volume of a cube or cuboid is length times width times height. So we swap the length for 30 minus 2x with brackets. We swap the width for 30 minus 2x with brackets. And we swap the height for x with brackets. So volume, V, equals 30 minus 2x multiplied by 30 minus 2x multiplied by x. Now 30 minus 2x multiplied by 30 minus 2x will give us 900 minus 120x plus 4x squared. And then we bring down that x with brackets around it as well. So 30 times 30 is 900. 30 times minus 2x is minus 60x. And minus 2x times 30 is minus 60x. And minus 60x minus 60x is minus 120x. And then minus 2x multiplied by minus 2x is plus 4x squared, because a minus by minus is a plus, and 2x times 2x is 4x squared. So we have 90 minus 120x plus 4x squared, and now we have to multiply all of this by x. So 90 multiplied by x is 90x, minus 120x multiplied by x is minus 120x squared, and 4x squared multiplied by x is 4x cubed. So the volume is 900x minus 120x squared plus 4x cubed. So we're interested in the maximum volume. And whenever we are asked about maximum or minimum, we want to think we have to differentiate. So we're going to differentiate v with respect to x. So dv dx. Differentiate v with respect to x. And v is the volume. So 900x, what we do is we just cross off the x and we get 900. So the derivative of 900x is 900. Minus 120x squared. Well, we bring the power down in front. The 2 comes down in front. And we reduce the power by 1. So we have minus 2 times 120 is minus 240. And 2 take away 1 is 1. So you really just get minus 240x. And then 4x cubed, so we bring the power down in front. The 3 comes down in front. And we reduce the power by 1. So we have 3 multiplied by 4 is 12. And x to the power of 3 minus 1 is x to the power of 2. So dv dx, the derivative of v, the derivative of the volume, is 900 minus 240x plus 12x squared. So the next step, whether we're looking for maximum or minimum volume, is to let dv dx, to let the derivative equal 0. And then we solve to find the stationary points. So we solve for x. So this is dv dx, so we let it equal to 0. And we start off by simplifying. So we divide everything by 3. So let's start with the 12. So 12x squared divided by 3 is 4x squared. It's good to put the x squared first. Minus 240x divided by 3 is minus 80x. It's good to put the x second. And then 900 divided by 3 is 300. So we have 4x squared minus 80x plus 300 equals 0. So we can simplify again. We can divide each term now by 4. So 4x squared divided by 4 is 1x squared, or just x squared. Minus 80x divided by 4 is minus 20x. And 300 divided by 4 is 75. So get x squared minus 20x plus 75 is equal to 0. Or what we could have done at the start was just divided each term by 12. And we would have got straight here. So now we have x squared minus 20x plus 75 equals 0. So we put the x squared first, the x second, and then the constant third. So at this point now, we can use the minus b formula to solve, or we can factorize. So I'm going to factorize. So since I have an x squared here, I'm going to put an x in the front of both brackets. Since I have 75 here, I'm going to have to get the factors of 75. And I need to choose a factor pair that when I add them together, I get minus 20. So I'm going to go with 15 and 5. So 15 multiplied by 5 is 75. And minus 15 minus 5 is minus 20. So I have 15 and 5 in the back of the bracket, so it doesn't matter which one comes first. Since this is a plus, I know that these signs are going to be the same. And since this is a minus, I know they're both minus. So I have x minus 15 multiplied by x minus 5, and that's equal to 0. So if x minus 15 is equal to 0, then x is equal to plus 15 or positive 15. And if x minus 5 is equal to 0, then x is equal to positive 5 or plus 5. So now I have my two x values. So I know that these are my stationary points. So I know that at these points, at x equals 15 and at x equals 5, I have a slope of 0. But I don't know which one is a maximum and I don't know which one is a minimum. And I'm interested in the maximum because I'm interested in the maximum volume. So in order to figure out which is which, I have to get the second derivative. So the second derivative is written as d squared v dx squared, the second derivative. And it means I have to differentiate the first derivative. So this was our first derivative here. So differentiating 900, I just get 0 because there's no x. Differentiating minus 240x, I just cancel out the x and I have minus 240. And differentiating 12x squared, I bring the power down in front, the 2 comes down in front, and 2 multiplied by 12 is 24. and the power, which is 2, take away 1 is 1. So I'd really have x to the power of 1, which is just x. So what I've done here, to get this second derivative, I just differentiated the first derivative. So now I have the second derivative. And now what I'm going to do is to substitute each of the x values that I just worked out in place of that x. So let's start off with x equals 15. So at x equals 15, the second derivative is equal to minus 240 plus 24 multiplied by 15. So I'm just swapping that x there for 15. 24 times 15 is 360, and minus 240 plus 360 is 120. And 120 is greater than 0, it's positive. So we're not really interested in what number this works out to be, we're only interested in, is it positive or is it negative? So since we got a positive answer, our answer is greater than 0, we must have a local minimum at x is equal to 15. If we had got a negative answer here, it would tell us we had a local maximum at 15, but we don't. We have a positive, so we know we have a local minimum at x is equal to 15. So now we're going to do the same thing with x equals 5. We're going to substitute it into the second derivative, and we're going to see is our answer positive or negative. So from the previous slide, we worked out our two x values to be 15 and 5, and then we worked out the second derivative to be minus 240 plus 24x. We substituted the 15 in place of that x, and we got a positive answer, which means that at x is equal to 15, we have a minimum. So now we need to do the same with x is equal to 5. So we swap the x in the second derivative for 5 with brackets around it. So at x is equal to 5, the second derivative is equal to minus 240 plus 24 times 5. 24 times 5 is 120, and minus 240 plus 120 is minus 120, which is less than 0, which is negative. So therefore, since we have a negative result, therefore there is a local maximum at x is equal to 5. So when we subbed 15 into our second derivative, we got a positive answer, and if you get a positive result, that means you have a local minimum. And when we subbed x is equal to 5 into the second derivative, we got a negative result, which means we have a local maximum. And that's what we're interested in. We're interested in the maximum volume. So therefore, we go with x is equal to 5. So the required dimensions for the maximum volume using x equals 5 is going to be, for the length, 30 minus 2 times 5, which is 20 centimetres. So we know that this is the length. So 30 minus 2x becomes 30 minus 2 multiplied by 5. So we swap the x for 5 at brackets. And 30 minus 2 times 5 is 30 minus 10, which is 20 centimetres. So the maximum length here is going to be 20 centimetres. The width was the same, 30 minus 2x. So for the width, 30 minus 2 times 5 again, which again is 20. So the width is 20 for the maximum volume. And then for the height, well, the height was just x. So the height must be just 5. So in order to get the maximum volume of this cuboid, we have to have a length of 20 centimetres, a width of 20 centimetres, and a height of 5 centimetres. If the question had not asked for maximum volume, if the question had asked for minimum volume, then instead of subbing 5 in place of the x, we would be subbing in 15 in place of the x. So it would have worked out to be 30 minus 2 times 15, and 2 times 15 is 30, so 30 minus 30 is 0, so we would have had a length of 0. The same for the width, would have had a width of 0, because we would have swapped this for 15, and then the height would have been 15. But obviously you couldn't actually construct a cuboid with a length and a width of 0. So part 2 says, what is the maximum volume of the box? So we worked out, for the maximum volume, we need a length of 20 centimetres, a width of 20 centimetres, and a height of 20 centimetres. So we just multiply these three values together, because volume is length times width times height. So the maximum volume of the box is the length times the width times the height, which is 20 by 20 by 5, which is 2000 centimetres cubed. For volume, we always have cubed. Another way of doing it would be to take the volume equation, or the volume formula that we worked out earlier on. So we said that volume equals 900x minus 120x squared plus 4x cubed. And since we got x is equal to 5 for the maximum volume, we swap each of those x's for 5 with brackets around it, and multiplying out, we get 2000 centimetre cubed, just like before.